Yeah, this talk will mainly, I want to talk about some recent results with the landscape function. Um, so here, and I have to do this kind of quickly, the kind of setup, but first I want to describe what the landscape function is. So the landscape function is used to, or has been used in recent years to study results in Anderson localization. Anderson localization is a phenomenon studied first described by this professor Philip Anderson in physics, who described that when the potential V in a Schrödinger operator has random values, say for instance in this you have a square is your domain, and the black spots here represent the values of V where V is equal to 1, and the white spot is where V is equal to 0. So you can think that on each little square, the value of V is given as 1 with probability 1/2 and 0 with probability 1/2. Then when you look at the eigenfunctions of the operator L, they will have this phenomena where they will be like, they will have this spike in some localized part of the domain, and then outside of that spike, it decays very, very fast. And this happens for many of the first eigenfunctions. So the landscape function, so this phenomenon has been studied heavily in mathematical physics for several decades. The landscape function, on the other hand, is a recent tool introduced in 2012 by physicist Marcel Filoche and Filoche-Mayboroda, my advisor. And basically, it's a function u which solves the equation minus delta u plus vu equal 1. So this thing magically, quote unquote, predicts where the eigenfunctions will localize. So in certain sense, so for instance, here you have again the same values of V, but then you can describe these values using U at certain energy levels, and then when you study the eigenfunction at the energy level, it will localize in one of the values given by U, by 1/U, essentially. So these are numerical results, and they are very, they seem very precise, numerically speaking, and this works for first few eigenfunctions. But there are also mathematical results showing the exponential decay of eigenfunctions in terms of an Angmon distance that uses the landscape function. This is a recent result in 2019 of Edo Garnol, Guy David, Marcel Filoche, David Jerison, and Filoche-Mayboroda. And another also very, very interesting thing about landscape function is how it can be used to study the distribution of eigenvalues. Right? So in mathematical physics, for a long time, even in the times of Hilbert, it was an important question to know what are what is the asymptotics of the eigenvalues for the Laplace equation, right? For harmonic function. But ever since then, it's been also studied for Schrödinger operators, the more complicated things. Of course, the most classical result is Wiles' law. But these are all asymptotic results in mathematics. But we also care about non-asymptotic bounds that also tell you what happens at the bottom of the spectrum, at the beginning of the spectrum. So in these few pictures, you basically have examples where the black lines represent basically the actual eigenvalue counting function, which tells you at any given lambda, it tells you how many eigenvalues there are below lambda, right? And then the green lines represent what the Wiles law would give you classically, and that, you know, mathematically there's a theorem that they converge asymptotically. So you send the energy to infinity, these lines will match. But the interesting thing is that when you use a slightly changed version of Wiles' law, where you introduce 1/U, where U is the landscape function, we call that, in this case, we're calling it W in these pictures, then you see that it really tracks the eigenvalue cutting function much more closely. So this has several applications in physics, so that's why it continues to be studied now. And one of the main, and others, there's also recent mathematical theorems making this a bit more precise, although they don't necessarily capture the full strength of these numerical results. A big tool, a big reason as to why the landscape function works so well, or something that explains a bit of the magic, is really that you have this conjugation. This is you just prove it using algebra, and so it is not too hard, but the point is that you can convert the full energy of the system, which is here on the right-hand side, to this energy here. And the idea is you conjugate it with u, right? You conjugate it by 1 over u, the operator, the Schrödinger operator. And now when here, the thing is you can just drop the last term on the first term on the left-hand side, and that gives you this inequality, which is really what is driving a lot of these estimates, the non-asymptotic bounds on the eigenvalue counting function, and exponential decay estimates. All of that is really being driven by these two inequalities, because we have tools of Schmoll-Agmon from a while back, and the techniques of Feerman, and basically combining those tools with these estimates, we can obtain, well, they obtain these results. Now, this has been extended beyond Schrödinger operator to other models, like the type bandit model for the Schrödinger operator, basically is a discrete Schrödinger operator, and also for random and matrices. There is an interesting extension of these ideas. Okay, now some questions I want to focus on in this talk is as follows. This exponential decay of eigenfunctions has been studied for several decades. How does the landscape function, which is a more recent tool, fit within this literature? Like, does it compare with other tools introduced there? Now, related to this question is that the exponential decay with the landscape function is always expressed in terms of an Agmon distance, which is this weighted distance by the square root of 1 over u. And basically, when I say there's exponential decay with the landscape function, I mean there's exponential decay in this Agmon distance, in this distance. But this distance in principle can be very degenerate if we don't have any information about what 1 over u is. So what conditions would you put on V, or what conditions on V would guarantee that it is related to Euclidean distance? Of course, in the case of random Schrödinger operators, the decay that we see, for instance, in the numerical experiments, is really Euclidean distance. And in Anderson localization, in the mathematical study of this, it's also Euclidean distance, the decay. So it should be, in principle, able to relate. But maybe if random Schrödinger operators is too hard, and at the moment it hasn't been done yet for random Schrödinger operators, maybe what about even more classical conditions of V? Can we relate the Agmon distance to Euclidean distance in non-trivial settings? Okay, and then another thing is that I said the idea has been extended to other models, but for a while it was also interesting to consider extending it to magnetic Schrödinger operator, which is also heavily studied in mathematical physics. And here the thing is that we introduce a magnetic field, and that is being described by this boldface A here, which is the magnetic potential, whose curl is the magnetic field. But the problem is that if you try to do a similar algebra, it doesn't work. It just doesn't work. This is really like a system because its solutions are complex valued, and you don't really get the conjugation that you got before. So you don't get an estimate like this, at least not quick, not easy. And so because you don't get an estimate like this, it has not been clear what to do with magnetic Schrödinger operator. Now, for the rest of the talk, I will talk basically about at least some partial answers to some of these questions. So to do this very quickly, I want to specify the conditions that I'm going to put on the potential on V, the zeroth order term in the equation. And I'm just going to ask that it is in a reverse order class of a certain exponent. Of course, reverse order class just means the way it satisfies a reverse order inequality is related to the Munkenhausen IP weight. And examples include positive polynomials, x to the alpha, where alpha can be negative up to some number. But what I really wanted to emphasize is that non-examples, among many other things, are random Bernoulli potentials. So this classical setting that I will describe does not work with the random Bernoulli potentials. And so a lot of the results I will talk, you can generalize them to a slightly bigger setting, but still it will not include random potentials. Okay, but in this classical setting of studying the reverse Holder potentials, Shen in the 90s introduced what has come to be known as the critical radius function. This is the function m of x, defined in this way. Easier to define it by reciprocal. It is the largest radius so that this quantity remains controlled. Look, heuristically, what it means is that at each point, it gives you the radius, 1 over m gives you the radius of a ball, such that on that ball, you can consider the Schrödinger operator as a perturbation of the Laplacian in quantitative ways. Okay, and then outside of that ball, the effects of the zeroth order term V take over and just drive the rest of the behavior. So it is, this was used by Shen to adapt the Feerman-Phong uncertainty principle, which they first used for polynomial V. But the gist of it is that he can obtain this estimate, this uncertainty principle. You will see a similarity between this estimate right here and the one over here that I wrote for the landscape function. It's basically 1 over u is in here with no constant, whereas in here there is some constant, and now it's m squared here on the left hand side. It's a different potential energy. Essentially, whenever you have an uncertainty principle, some lower bound for the total energy of the system, then you will, many times it is possible to prove exponential decay in a Hammond distance given by the weight over here. The easiest thing you can do is just write V here, for instance, right? Because you can, of course, bound this below by the integral of Bf squared. But that is not so helpful, does not give you the most precise results. M will give you, essentially because of this picture. See, if V, because the potential can be 0, right? 0 on some parts of the domain, and then if you have an Hammond distance in this white part where V is 0, then the Hammond distance will not differentiate these two points x and y. However, if B is 0 in this white region and it's very large, say in these other regions which are close, the function m will see those larger regions and will take those values. And so it gives you the correct weight to give exponential decay of solutions. So that's why it was used to show the exponential decay of eigenfunctions in the Hammond distance, now with m squared, not with 1 over u. Remember, this was in the 90s. So there was no landscape function yet. No one was using that yet. In fact, for the fundamental solution, okay, of the equation, you have a kind of more precise estimate, which is an upper bound and lower bound by the same exponential decay in the same quantities, except with different constants, possibly. Right, so you have epsilon 1 here, epsilon 2 here, but this Hammond distance is the same. Now, this, as it turns out, and the reason why Shen studied this kind of estimate is because of applications to harmonic analysis. Because at that time, they were interested in studying the LP bounds for the Riesz transforms associated to the Schrödinger operator, such as these ones. Okay, but also others, or proving the Calderon-Sigmund properties of certain kernels. associated to the Schrödinger operator once again. But that, in order to do that, a main step first is to prove that the fundamental solution has fast enough decay. And so, in fact, if some very large polynomial decay is enough, but if you, in fact, you have exponential decay in this setting. And then this was then using this critical radius function of Son-Wei-Shen. The other authors continued this work in the last decade and even currently to extend, for instance, the Mukenhab weights to this setting. So it is in this respect that the critical radius function has been used in harmonic analysis a lot. So it's just like it's a correct function to work with Schrödinger operators that have reverse order potentials. Now, and then there are also results of non-asymptotic Blason eigenvalue quantity functions with this critical radius function, also exponential decay for heat kernel, and many similar results for the magnetic Schrödinger operator. So now a thing is that I've told you that you can use that critical radius function m, and you can use 1 over u to study the exponential decay and eigenvalue quantity functions and all these properties of Schrödinger operators. What is the relationship between them? Is one better than the other? Okay, or are they not comparable? Well, in fact, they are comparable. They are pointwise equivalent. So assuming that you're in 3 dimensions or more, and V is in a reverse order class, n over 2, and U is landscape function on Rn, which exists. It's just a technical point in this case. But then there is a constant, and you can compare them. They're pointwise equivalent. So there are several corollaries of this. The first that I want to say is that, therefore, the sharp exponential decay of the fundamental solution can also be written in terms of Agmon distance with 1 over u. Since they are pointwise equivalent, now these Agmon distances are essentially the same up to a constant, right? So, okay. And then it means also that the landscape function inherits a lot of properties that the critical radius function has. But this, we don't have to go into too much detail. I just want to say that, for instance, number 2 here is a sort of Harnack inequality, but it is much stronger than what the usual argument for Harnack inequality would give you. Okay, so it just gives you a stronger result in this case. And then 3 here is what's really telling you that, because if you integrated this, if you brought Agmon distance using these estimates, it will tell you that the Agmon distance with 1 over u is comparable to powers of the Euclidean distance. So it is showing that in the case where V is a reverse order potential, the Agmon distance is remembering Euclidean distance, right? It is related to it after all, because there are some situations where they need not be comparable at all. So this is telling you, it is like a result that tells you that they are in fact equivalent in these settings. Now, and this is just a technical slide that if someone wants to, if the domain were bounded, then its solution to this is just like Lax-Milgram. If it's unbounded, then it's not clear, because 1 is not a function you can use Lax-Milgram with. But you can give equivalent conditions, basically asking the green function has enough decay, and that will be it. So, and that is satisfied when V is in reverse order class, and it's not identically 0. Now, what about the magnetic Schrödinger operator, which is the thing in the title? Well, in here, again, you have magnetic field. As I said, is the curl of the magnetic potential. In 3 dimensions or more, it's just an antisymmetric matrix given by this matrix here. And now what I want to say is consider, remember I said there was difficulty with the algebra of magnetic Schrödinger operator. What I want to say is make a trick, do a trick. Where now I'm saying consider a landscape function u not related first to this equation, but just given by this Schrödinger operator. So you see, it's the landscape function for an operator with a potential b plus absolute value of b, where absolute value of b, but what I mean by this is just the sum of the absolute values of all the components of b. Okay, and then put the really boundary conditions. If you're in Rn, then don't worry about this. Right, and now the theorem, which is an uncertainty principle, and remember I said this is essentially what you need in order to prove exponential decay estimates and so on. So from this, you can really get a lot of stuff. Is I can do this assuming that no component of the magnetic field changes sign, which generalizes certain things that have been done in 2 dimensions, but it was, for a long time, it's not clear what to do in 3 dimensions or more. And what I'm saying is that if the component of B, no component of B changes sign, then this is true. By the way, you can also ask this possibly after a rotation, and you can generalize this assumption even more, but we don't have too much time to talk about that. But I do want to say that this result in general is not sharp, because in fact, this kind of estimate will give you exponential decay. It's a sort of linear exponential decay, but the decay given by magnetic field is often Gaussian. For instance, when magnetic field is constant. And so these results are not extremely sharp, at least not those ones. But there are certain sharp things you can get, like non-asymptotic bounds on the eigenvalue counting function. So here I just want to say what the chance problems are. Is that in 3 dimensions, Phong-Shen prove that this non-asymptotic eigenvalue bounds on the eigenvalue counting function. Here, basically, this is the eigenvalue counting function, and n tilde is just a counting function that counts the number of cubes in the correct side length, such that this energy will be small compared to the energy. Okay. So he's saying, to bound eigenvalue counting function, just count these things, and that gives you these non-asymptotic bounds. But the thing is, he has that B plus B is in reverse order, which is the natural condition you want to make if you're using the critical radius function. So that's fine. But it was also asked this condition in blue here on the gradient of magnetic field. So as you see, this is like a quantitative condition. On gradient of magnetic field, which is one more derivative than what it should be asked, and then the critical radius function here appears. So this is hard to verify, and essentially the only examples known were positive polynomials. Okay, so but Chen's problem is to remove the assumption on the gradient of magnetic field, because he was able to do that in 2 dimensions. See, in 2 dimensions, he just asked that the magnetic field doesn't change sign, and then he able to obtain it with no assumption on the gradient of magnetic field. But then in 3 dimensions and more, it was open. And then he had a similar result for the negative eigenvalues and similar question. Now in this case, not too much time to, well, the point is he gave this upper bound on the eigenvalue counting function, but the point is he used again this assumption, same assumption, which he said it seemed too strong, but it appears that some assumption on gradient of magnetic field seems necessary to obtain this result, this bound on the eigenvalue counting function. So again, I said there's the 2 problems, and the conjecture basically related to removing this assumption 1 here. This assumption has also appeared in other works to study exponential decay of the eigenfunctions and the fundamental solution, and even for the bounds on Riesz transforms. So the theorem, well, this is not written with full details, but the point is that you don't need any assumption on the gradient of magnetic field to obtain these bounds or the other results in the literature. They all follow from corollaries of this previous theorem I had here. Well, corollaries of this uncertainty principle and the machineries of each of these papers, right? Like you still need to do whatever they did, but why is that true? Because the reason that Phong-Shen needed this assumption and everybody else is because this was the assumption to make the uncertainty principle true in the case of magnetic Schrödinger operator. But since I'm telling you that I can get an uncertainty principle without this assumption, then that bypasses that, and then I just need to make sure that this assumption is not used anywhere else in the proof. So in many cases that was true, and so by assuming certain directionality assumptions, which is what I said, no component on B changes sign, then you can recover the same results of Phong-Shen. And this is really the recap of what I said last slide. So you have magnetic Schrödinger operator and assume that no component of the magnetic B changes sign. And assume that B plus B is in reverse Euler class, the natural assumption, and omega is silent. Now again, you do the trick. You don't consider for the landscape function, you don't take the magnetic Schrödinger operator, but you take this related Schrödinger operator, minus delta plus d plus v. And you consider its landscape function for L tilde. Then you have this result. And that's just from the previous theorem I showed. So this is the energy of the magnetic Schrödinger operator now, but this U is the landscape function related to this operator L tilde. Now, the point is that I also showed that 1 over U is comparable to M squared, right? The point was equivalent. So on the left-hand side, I can just replace with M squared. And see, that gives the uncertainty principle for the magnetic Schrödinger operator. But at no point, I needed to assume this assumption 1, which was like a key assumption to make this estimate true in the previous papers. So then, for instance, the theorems of Song-Wei-Shen and Kazuhiro Kurata and Besma Ben Ali and Mayboroda and myself, all of these will follow from basically using this proof now. So I'm trading, okay, final thing, I'm trading the assumption on the gradient of magnetic field, this assumption 1, with just a directionality assumption on the magnetic field, all right? Which basically is telling you, for instance, in 3 dimensions, that the components of the magnet, in 3 dimensions where the magnetic field is just a vector, it can be restated as saying that this is true for every x and y, right? Or in the domain. So that all of the values of magnetic field reside in a cone in R3, in a 90-degree cone. And that is it. Thank you very much for listening. Yeah.